Question 1. During the evaluation of a complex weather diversion scenario, the ATP pilot notices the first officer appears hesitant and expresses a slight concern about the proposed reroute, citing a potential for increased turbulence. The ATP pilot, under pressure to maintain the schedule and aware of the limited time for decision-making, considers several responses. Which approach best demonstrates effective crew resource management, CRM, in this situation? Option A. Proceed with the initially planned diversion route, informing the first officer that the schedule is critical and that minor turbulence is an acceptable risk for an ATP-rated pilot to manage. Option B. Briefly listen to the first officer's concern, but then confidently state the chosen route is the most efficient and instruct the first officer to prepare for the diversion, implying their input is not essential for this decision. Option C. Immediately override the first officer's concern by stating that as the pilot in command, their judgment is final and that any further discussion on the matter is unnecessary. Option D. Acknowledge the first officer's concern, ask for specific details about their assessment of the turbulence, and collaboratively discuss alternative routing options or mitigation strategies, ensuring a shared understanding of the risks and the final decision. Correct answer is D. Acknowledge the first officer's concern, ask for specific details about their assessment of the turbulence, and collaboratively discuss alternative routing options or mitigation strategies, ensuring a shared understanding of the risks and the final decision. Explanation. This scenario is professionally challenging because it requires the ATP pilot to balance immediate operational demands with the long-term safety implications of crew performance. The pressure to maintain schedule and avoid delays can create a conflict with the need for thorough CRM practices. Careful judgment is required to ensure that safety is not compromised for expediency. The correct approach involves actively engaging the first officer in the decision-making process, seeking their input, and ensuring they understand the rationale behind the chosen course of action. This aligns with the core principles of crew resource management, specifically emphasizing teamwork and communication. By fostering an environment where the first officer feels empowered to contribute and question, the ATP pilot upholds regulatory expectations for effective crew coordination and shared situational awareness, which are critical for preventing errors and enhancing overall flight safety. This proactive engagement directly supports the FAA's emphasis on CRM as a fundamental component of safe airline operations, as outlined in advisory circulars and training requirements. An incorrect approach that involves unilaterally making decisions without seeking input from the first officer fails to leverage the collective knowledge and perspective of the flight crew. This undermines teamwork and can lead to a degradation of situational awareness for the entire crew, as the first officer may not fully grasp the nuances of the situation or the reasoning behind the pilot's actions. Ethically, it represents a failure to lead and mentor, potentially creating a hierarchical dynamic that discourages open communication. Another incorrect approach, which is to dismiss the first officer's concerns without proper consideration, directly contradicts the principles of effective communication and teamwork. This can lead to the first officer withholding valuable information or insights in the future, thereby diminishing the crew's ability to manage complex situations. It also creates a negative crew environment, which is detrimental to morale and long-term safety performance. From a regulatory standpoint, it can be seen as a failure to adhere to CRM training mandates that stress the importance of respecting and integrating all crew members' contributions. A third incorrect approach, which is to proceed with a plan that the first officer has expressed reservations about without a clear and shared understanding of the risks and mitigation strategies, demonstrates poor decision-making and a lack of collaborative problem-solving. This can lead to a situation where the crew is not operating with a unified understanding of the operational plan, increasing the likelihood of errors. It also fails to meet the ethical obligation of ensuring all crew members are comfortable and confident with the flight plan, especially when safety is a concern. The professional decision-making process in such situations should involve a structured approach to communication and problem-solving. The ATP pilot should first actively listen to and acknowledge the first officer's concerns. Then, they should clearly articulate their own assessment of the situation and the proposed plan, inviting further discussion and clarification. If disagreements persist, a collaborative risk assessment should be conducted, exploring alternative solutions and their respective implications. The ultimate decision should be based on a shared understanding of the risks and a consensus on the safest course of action. Or if consensus cannot be reached, the ATP pilot must make a clear, well-reasoned decision, ensuring the first officer understands the rationale and any associated risks. Question 2. Benchmark analysis indicates that during cruise flight, an unexpected intermittent warning light illuminates on the primary flight display related to a non-critical hydraulic system, accompanied by a minor fluctuation in the associated system pressure gauge. Which of the following represents the most professionally sound and regulatory compliant approach for the ATP airplane pilot? Option A. Immediately initiate a descent to a lower altitude and request a diversion to the nearest suitable airport to address the hydraulic system anomaly. Option B. Continue the flight at the current altitude and speed, monitoring the hydraulic system closely, and consult the aircraft's Quick Reference Handbook, QRH, or electronic checklist for the specific warning light and associated procedures. Option C. Immediately change the aircraft's flight path to avoid potential areas of turbulence that might be exacerbating the hydraulic system issue. Option D. Inform passengers of a potential hydraulic system issue and advise them to prepare for an emergency landing. The correct answer is A. Immediately initiate a descent to a lower altitude and request a diversion to the nearest suitable airport to address the hydraulic system anomaly. Explanation. Scenario analysis. This scenario presents a professional challenge for an airline transport pilot at airplane due to the critical nature of maintaining situational awareness and adhering to established procedures when encountering unexpected aircraft system behavior during a critical flight phase. The challenge lies in balancing the immediate need to address a potential system malfunction with the paramount responsibility of ensuring flight safety, passenger well-being, and compliance with air traffic control instructions. The pilot must exercise sound judgment, drawing upon extensive training and knowledge of aircraft systems and regulations to make timely and accurate decisions under pressure. Correct approach analysis. The correct approach involves a systematic and procedural response to the unexpected system indication. This includes immediately cross-referencing the primary flight display, PFD, with the engine indicating and crew alerting system ICAs, or electronic centralized aircraft monitor, ECM, to confirm the anomaly and identify the specific system involved. Following this, the pilot must consult the appropriate aircraft checklist for the identified malfunction. This methodical process ensures that all necessary steps are taken in a logical order, minimizing the risk of overlooking critical actions or exacerbating the problem. This approach is directly supported by Federal Aviation Regulations, FAR, specifically 14 CFR 91-13A, which mandates that no person may operate an aircraft in a careless or reckless manner so as to endanger the life or property of another. Furthermore, it aligns with Standard Operating Procedures (SOP) and the Principles of Crew Resource Management (CRM), which emphasize standardized responses to emergencies and malfunctions to ensure crew coordination and effective decision-making. Incorrect approaches analysis. An incorrect approach would be to immediately initiate a significant aircraft maneuver, such as a rapid descent or turn, without first confirming the nature and severity of the system anomaly through cross-referencing displays and consulting the relevant checklist. This action bypasses critical diagnostic steps and could lead to unnecessary passenger discomfort, potential loss of control if the maneuver is inappropriate for the actual malfunction, or a diversion of attention from other critical flight parameters. This violates the principle of operating an aircraft in a safe and orderly manner, as stipulated by 14 CFR 91-13A. Another incorrect approach would be to ignore the system indication and continue the flight as if no anomaly occurred, especially if it does not immediately impact controllability. This demonstrates a failure to acknowledge and address potential safety of flight issues, which is a direct contravention of the pilot's duty to maintain the aircraft in an airworthy condition and to operate it safely. Such an approach could lead to a more severe system failure later in the flight, potentially compromising the safety of the aircraft and its occupants. This also fails to uphold the professional responsibility to proactively manage aircraft systems. A third incorrect approach would be to rely solely on memory items for the suspected malfunction, without consulting the official aircraft checklist. While memory items are crucial for immediate actions in certain emergencies, complex or less common malfunctions require the detailed, step-by-step guidance provided by the written checklist to ensure all necessary actions are performed correctly and in the proper sequence. Relying solely on memory can lead to omissions or errors, particularly under stress, and deviates from established safety protocols designed to mitigate risk. Professional reasoning. Professionals in this situation should employ a structured decision-making process. First, recognize and acknowledge the anomaly. Second, gather information by cross-referencing relevant aircraft systems displays. Third, consult the appropriate checklist to understand the nature of the malfunction and the prescribed actions. Fourth, communicate with the other crew member, if applicable, and air traffic control as necessary. Fifth, execute the checklist procedures diligently. This systematic approach, rooted in regulatory compliance and best practices like CRM, ensures that decisions are informed, safe, and effective, prioritizing the well-being of all on board. Question 3. Stakeholder feedback indicates that some pilots are making go/no-go decisions based on incomplete weather assessments. As an airline transport pilot, you are presented with a TAF for your destination showing marginal VFR conditions, a surface analysis chart indicating a developing frontal system approaching the route, and a PIRP from an aircraft that encountered moderate turbulence approximately 100 miles from your destination. Which approach best demonstrates adherence to regulatory requirements and professional judgment for determining flight safety? Option A. Proceed with the flight, as the TAF indicates marginal VFR, assuming the frontal system and PIRP are not significant enough to warrant a delay. Option B. Focus solely on the destination TAF and proceed if it remains within operational limits, as en route weather is less critical than destination conditions. Option C. Delay the flight and request an updated weather briefing, specifically asking for clarification on the potential impact of the frontal system and the severity of the reported turbulence. Option D. Depart as scheduled, but plan to deviate around the frontal system if encountered and disregard the PIRP as it is from a single aircraft. The correct answer is A. Proceed with the flight as the TAF indicates marginal VFR, assuming the frontal system and PIRP are not significant enough to warrant a delay. Explanation. This scenario is professionally challenging because it requires the pilot to synthesize information from multiple, potentially conflicting, weather sources and make a critical go/no-go decision under pressure, balancing safety with operational efficiency. The pilot must not only understand the individual weather products, but also their interrelationships and implications for flight safety. The correct approach involves a comprehensive review of all available weather products, prioritizing official forecasts and reports, and cross-referencing them to identify areas of uncertainty or potential conflict. This includes analyzing surface analysis charts for frontal systems, weather depiction charts for general conditions, radar and satellite imagery for convective activity and cloud cover, and then correlating these with METR, TAF, SIGMET, AIRMET, and convective SIGMET. The pilot must then apply their judgment to determine if the forecast conditions, as represented by these products, are within the aircraft's and crew's operational capabilities and safety margins. This aligns with the fundamental regulatory requirement for pilots to be thoroughly familiar with all available weather information pertinent to their flight, and to exercise sound judgment in determining if flight is safe. The ethical imperative is to prioritize the safety of passengers and crew above all else. An incorrect approach would be to rely solely on a single weather product, such as only reviewing the TAF for the destination airport, without considering broader weather patterns or en route conditions. This fails to meet the regulatory requirement of being thoroughly familiar with all pertinent weather information and ignores potential hazards indicated by other sources like SIGMET or radar. Another incorrect approach is to dismiss a weather advisory, such as a SIGMET, based on a subjective feeling that it might not be accurate or severe. This demonstrates a failure to respect the expertise of meteorologists and the regulatory weight given to such advisories, potentially leading to flight into hazardous conditions. Finally, an approach that prioritizes schedule adherence over a thorough weather assessment, making a decision to depart without fully understanding the implications of all weather data, is a direct violation of the pilot's primary responsibility for safety and a failure of professional judgment. Professionals should employ a structured decision-making framework that begins with information gathering, collecting all relevant weather products, followed by analysis, cross-referencing, identifying trends and conflicts, evaluation, assessing risks against operational capabilities, and finally, decision-making, a go/no-go or altered plan decision based on the risk assessment. This iterative process ensures all factors are considered and promotes a safety-first mindset. Question 4. Comparative studies suggest that while pilots are trained to interpret various wind phenomena, the most critical factor in mitigating risks associated with surface winds, upper-level winds, wind shear, mountain waves, and turbulence is the pilot's proactive integration of real-time data with predictive information. Considering the U.S. regulatory framework for airline transport pilots, ATP Airplane, which approach best exemplifies the required professional judgment and adherence to safety protocols when encountering or anticipating these wind-related hazards. Option A. Prioritizing adherence to the planned flight path and altitude, relying solely on pre-flight forecast models for wind conditions, and only deviating if a direct and immediate threat is visually confirmed. Option B. Dismissing any reported turbulence from other aircraft as subjective and potentially exaggerated, and continuing on the planned route unless onboard systems indicate a critical failure. Option C. Actively seeking and evaluating pilot reports, PIRE, cross-referencing them with onboard weather radar and predictive wind shear systems, and making timely deviations in altitude or course based on this integrated, real-time assessment to avoid hazardous conditions. Option D. Focusing primarily on surface wind information for en route flight planning, as this is most relevant for aircraft control, and considering upper-level winds only if they significantly impact fuel burn calculations. The correct answer is A. Prioritizing adherence to the planned flight path and altitude, relying solely on pre-flight forecast models for wind conditions, and only deviating if a direct and immediate threat is visually confirmed. Explanation. Scenario analysis. This scenario presents a professional challenge for an airline transport pilot at airplane due to the inherent unpredictability and potential severity of atmospheric phenomena. The pilot must synthesize information from various sources, including forecasts, pilot reports, and onboard systems, to make critical decisions regarding flight path and operational safety. The challenge lies in balancing the need for efficient flight operations with the paramount responsibility of ensuring the safety of passengers and crew, especially when encountering or anticipating hazardous wind conditions. This requires a deep understanding of meteorological principles and their practical application in aviation. Correct approach analysis. The correct approach involves a proactive and comprehensive assessment of all available wind-related data, including surface winds, upper-level winds, and forecasts for wind shear and turbulence. This includes actively seeking and evaluating pilot reports, PIRE, and utilizing onboard weather radar and predictive wind shear systems. The pilot must then integrate this information with the aircraft's performance characteristics and the specific operational context, e.g., departure, en route, approach, landing. Regulatory frameworks such as those found in the U.S. Federal Aviation Regulations, FAR, specifically 14 CFR Part 91 and Part 121, mandate that pilots maintain a safe altitude and airspeed, avoid hazardous weather, and exercise good judgment. The correct approach aligns with these regulations by prioritizing safety through diligent information gathering and informed decision-making, ensuring that deviations from planned routes or altitudes are made when necessary to avoid hazardous conditions like severe turbulence or wind shear. Incorrect approaches analysis. An approach that relies solely on surface wind information for en route flight planning is critically flawed. This ignores the significant impact of upper-level winds on aircraft performance, fuel consumption, and the potential for encountering jet streams or other high-altitude wind phenomena that can affect the flight. It also fails to account for wind shear, which is most dangerous during takeoff and landing, but can also occur at higher altitudes. An approach that dismisses pilot reports of turbulence as anecdotal and relies exclusively on forecast models is also professionally deficient. While forecast models are valuable, PIRE provide real-time, specific information about actual conditions encountered by other aircraft. Ignoring this direct feedback can lead to flying into areas of unexpected and severe turbulence. Regulations emphasize the importance of utilizing all available information, including PIRE, to ensure safety. An approach that prioritizes maintaining a predetermined flight path regardless of reported or forecast hazardous wind conditions demonstrates a failure to exercise good judgment and adhere to the principle of avoiding hazardous weather. This approach prioritizes schedule adherence over safety, which is a direct contravention of pilot responsibilities and regulatory mandates to operate aircraft safely. Professional reasoning. Professionals in this role should employ a systematic decision-making process that begins with thorough pre-flight planning, incorporating all available meteorological data. During flight, this process involves continuous monitoring of weather information, active solicitation and evaluation of pilot, and vigilant observation of onboard weather systems. When encountering or anticipating hazardous wind conditions, the pilot must prioritize safety by making timely and appropriate deviations in altitude, course, or airspeed, communicating these deviations to air traffic control and the cabin crew, and documenting the event as required. This iterative process of information gathering, assessment, decision-making, and action, guided by regulatory requirements and professional judgment, is essential for safe flight operations. Question 5. Stakeholder feedback indicates a recurring concern regarding pilot decision-making when faced with intermittent environmental control system malfunctions during long-haul flights. Specifically, pilots are sometimes hesitant to initiate diversions for issues that do not immediately present as catastrophic. Considering the regulatory framework for airline transport pilot at airplane operations, what is the most appropriate initial course of action when an intermittent cabin pressurization warning light illuminates, accompanied by a noticeable change in cabin altitude, but without a complete loss of cabin pressure or oxygen? Option A. Continue the flight to the destination, monitoring the system closely and advising passengers to remain calm. Option B. Attempt to reset the pressurization system using non-standard troubleshooting techniques to see if the warning light extinguishes. Option C. Immediately initiate a diversion to the nearest suitable airport, declaring an emergency. Option D. Consult the Aircraft Flight Manual AFM, or Pilot's Operating Handbook PO, for the specific procedure related to the warning light and cabin altitude change, and communicate the situation to air traffic control and the cabin crew to assess passenger comfort and potential oxygen needs. The correct answer is C. Immediately initiate a diversion to the nearest suitable airport, declaring an emergency. Explanation. Scenario analysis. This scenario presents a professional challenge for an airline transport pilot at airplane because it requires immediate decision-making regarding a critical aircraft system failure during a flight with passengers. The pilot must balance passenger safety, regulatory compliance, and operational feasibility. The challenge lies in accurately assessing the severity of the environmental control system malfunction, understanding its potential cascading effects, and implementing the most appropriate course of action without compromising the safety of flight. The pilot's judgment is paramount in determining whether to continue the flight, divert, or take other corrective measures, all while adhering to strict operational procedures and regulations. Correct approach analysis. The correct approach involves a systematic evaluation of the environmental control system malfunction, prioritizing passenger safety and regulatory compliance. This includes consulting the Aircraft Flight Manual AFM, or Pilot's Operating Handbook PO, for specific procedures related to the identified malfunction, assessing the impact on cabin pressurization, oxygen availability, and passenger comfort, and communicating effectively with air traffic control and the cabin crew. The pilot must then make a decision based on the severity of the issue and the aircraft's capabilities, which may involve a diversion to the nearest suitable airport if the malfunction poses a significant risk. This approach is justified by federal aviation regulations, FAR, specifically those pertaining to airworthiness and operational safety, which mandate that pilots maintain their aircraft in an airworthy condition and operate them safely. The FARs require pilots to be knowledgeable of their aircraft systems and to take appropriate action in case of system malfunctions. Incorrect approach is analysis. An incorrect approach would be to ignore or downplay the malfunction, assuming it will resolve itself or is not critical enough to warrant immediate attention. This is a direct violation of regulatory requirements to address any known airworthiness deficiencies. Such an approach could lead to a worsening of the situation, potentially compromising cabin pressurization or oxygen levels, thereby endangering passengers and crew. This failure to act constitutes a breach of the pilot's duty of care and regulatory obligations. Another incorrect approach would be to attempt complex, unapproved troubleshooting procedures without consulting the AFM/POH or without proper training. This could exacerbate the problem, potentially causing further damage to the system or creating new hazards. It bypasses established safety protocols and relies on guesswork rather than documented, tested procedures, which is contrary to the principle of operating within the aircraft's approved limitations and procedures. A third incorrect approach would be to continue the flight to the intended destination without assessing the full impact of the malfunction or considering a diversion, especially if the malfunction affects critical systems like pressurization or oxygen. This demonstrates a failure to prioritize safety and adhere to the principle of aviate, navigate, communicate in the face of a significant system issue. It disregards the potential for the problem to escalate and the impact on passenger well-being. Professional reasoning. Professionals in this situation should employ a structured decision-making framework. This typically involves 1. Recognition. Acknowledge the malfunction and its potential implications. 2. Assessment. Gather information about the malfunction's nature and severity, consulting relevant documentation AFM/PO. 3. Evaluation. Determine the impact on aircraft systems, safety, and passengers. 4. Decision. Choose the most appropriate course of action, e.g., continue with caution, divert, troubleshoot according to procedure. 5. Action. Implement the chosen course of action. 6. Communication. Inform relevant parties at cabin passengers if necessary. 7. Monitoring. Continuously assess the situation and adjust the plan as needed. This systematic approach ensures that all critical factors are considered, leading to the safest and most compliant outcome. Question 6. Investigation of a departure scenario where a significant crosswind, higher than standard temperature, and a slightly increased aircraft weight are present. What is the most appropriate decision-making approach for an airline transport pilot to ensure safe takeoff performance? Option A. Conduct a detailed performance calculation using the aircraft's approved airplane flight manual, AFM, data for the exact conditions, ensuring all safety margins are met or exceeded, and conservatively decide to delay or cancel the flight if performance is marginal. Option B. Consult with dispatch and other pilots for their opinion on whether the conditions are acceptable and base the decision on the consensus. Option C. Proceed with the takeoff if the runway length appears sufficient, prioritizing adherence to the flight schedule and minimizing passenger inconvenience. Option D. Rely on general experience with similar aircraft types and conditions, assuming the aircraft can handle the current situation with adequate safety margins. The correct answer is A. Conduct a detailed performance calculation using the aircraft's approved airplane flight manual, AFM, data for the exact conditions, ensuring all safety margins are met or exceeded, and conservatively decide to delay or cancel the flight if performance is marginal. Explanation. Scenario analysis. This scenario presents a professionally challenging situation for an airline transport pilot because it requires balancing operational efficiency with the absolute priority of safety, particularly when faced with conflicting pressures. The pilot must make a critical go/no-go decision for takeoff under non-standard conditions, where a slight misjudgment could have severe consequences. The challenge lies in accurately assessing the combined effects of multiple performance-degrading factors and making a decision that is not influenced by schedule pressure or a desire to avoid delays. This demands a rigorous application of regulatory knowledge and sound judgment. Correct approach analysis. The correct approach involves a systematic and conservative evaluation of takeoff performance based on the prevailing environmental conditions and aircraft weight. This means meticulously calculating the required takeoff distance, climb performance, and other critical parameters, ensuring that all safety margins are maintained or exceeded. The pilot must consult and strictly adhere to the aircraft's approved performance data, as found in the Airplane Flight Manual AFM, or equivalent documentation, which is mandated by regulatory frameworks such as the Federal Aviation Regulations, FAR in the United States. Specifically, FAR 91/103b requires pilots to be familiar with all available information concerning the intended flight, including performance data. Furthermore, FAR 121/191 and related sections for scheduled operations emphasize that takeoff performance must be determined for the actual conditions, and the aircraft must be able to meet all performance requirements. A conservative approach, erring on the side of caution when conditions are marginal, is a cornerstone of professional aviation safety and aligns with the overarching principle of ensuring the aircraft is operated safely under all circumstances. Incorrect approach is analysis. An incorrect approach would be to rely on past experience or a general sense of the aircraft's capabilities without performing a precise calculation for the current conditions. This fails to acknowledge that takeoff performance is highly sensitive to variations in weight, altitude, temperature, and wind, and that a rule of thumb is not a substitute for regulatory compliance. Such an approach violates the pilot's responsibility to ensure the aircraft is capable of a safe takeoff under the specific circumstances, as required by regulations. Another incorrect approach would be to prioritize the schedule and attempt to push the limits of the aircraft's performance, assuming that the calculated margins are overly conservative. This demonstrates a failure to uphold the absolute priority of safety over schedule adherence, a fundamental ethical and regulatory tenet for all commercial pilots. Regulations, such as those found in FAR Part 121, explicitly prohibit operating an aircraft when performance limitations are exceeded, regardless of schedule demands. A third incorrect approach would be to make a decision based on the opinion of ground personnel or other pilots without independently verifying the performance data. While seeking input can be valuable, the ultimate responsibility for the go/no-go decision rests with the pilot in command, who must be able to justify their decision based on the aircraft's approved performance data and regulatory requirements. Delegating this critical judgment without independent verification is a dereliction of duty and a regulatory failure. Professional reasoning. Professionals in this situation should employ a structured decision-making framework that prioritizes safety and regulatory compliance. This framework typically involves 1. Information gathering. Obtain all relevant data, including current weight, forecast winds, temperature, pressure, altitude, and runway conditions. 2. Performance calculation. Meticulously calculate takeoff performance using the aircraft's approved AFM data for the specific conditions. This includes takeoff distance, accelerate stop distance, and climb performance. 3. Regulatory compliance check. Verify that all calculated performance parameters meet or exceed the minimum requirements stipulated by the applicable regulations, e.g. FAR Part 121 for scheduled operations. 4. Risk assessment. Evaluate the margins of safety. If margins are marginal or if there is any doubt about the accuracy of the data or the conditions, a conservative decision must be made. 5. Decision. Make a clear go/no-go decision based on the analysis. If the decision is no-go, communicate this clearly and professionally, providing the regulatory basis for the decision. 6. Documentation. Record the decision and the rationale, especially if it deviates from an initially planned operation. This systematic approach ensures that decisions are objective, data-driven, and compliant with all regulatory mandates, thereby upholding the highest standards of aviation safety. Question 7. Governance review demonstrates that a pilot preparing for an instrument flight rule, IFR, cross-country flight needs to obtain comprehensive weather information. Considering the roles of various aviation weather service providers, what is the most prudent and regulatory compliant approach for the pilot to gather this critical data? Option A. Only check the National Weather Service, NWS, public website for general weather conditions. Option B. Solely rely on the weather radar displayed on the aircraft's onboard navigation system. Option C. Contact a private aviation weather forecasting service for a personalized briefing. Option D. Obtain a pilot briefing from an automated flight service station, AFS, and review Aviation Weather Center, AWC, advisories and forecasts. The correct answer is D. Obtain a pilot briefing from an automated flight service station, AFS, and review Aviation Weather Center, AWC, advisories and forecasts. Explanation. This scenario presents a professional challenge due to the critical nature of aviation, weather information, and the pilot's ultimate responsibility for flight safety. The pilot must accurately interpret and utilize weather services provided by governmental agencies to make informed decisions, especially when faced with potentially hazardous conditions. The challenge lies in discerning the most reliable and appropriate source of information for a specific flight phase, and understanding the limitations of each service. The correct approach involves proactively consulting the Aviation Weather Center, AWC, for forecasts and current conditions, and then utilizing flight service stations, FSS, or automated flight service stations, AFS, for pilot briefings, and to obtain specific, localized weather information relevant to the intended route and destination. This aligns with the Federal Aviation Regulations, FAR, that mandate pilots to obtain weather information prior to flight and to remain aware of weather conditions throughout the flight. Specifically, 14 CFR 91, 103 requires pre-flight action to include reviewing weather reports and forecasts. The AWC provides the foundational meteorological products, while FSS/AFS offer the direct pilot interface for obtaining this information and clarifying any ambiguities. This layered approach ensures comprehensive situational awareness. An incorrect approach would be to solely rely on a single source without cross-referencing or understanding its primary function. For instance, solely consulting FSS/AFS without reviewing AWC products might lead to a lack of understanding of broader weather patterns or potential severe weather systems not immediately apparent in a localized briefing. Conversely, only reviewing AWC products without engaging FSS/AFS could mean missing critical, real-time updates or localized advisories that FSS/AFS are equipped to provide. Relying on non-official or outdated weather information sources would be a severe regulatory failure, violating the mandate to obtain official weather data and potentially compromising flight safety. Professional decision-making in such situations requires a systematic process. First, identify the need for weather information. Second, determine the most appropriate sources based on the flight phase and type of information required, e.g., en route forecast vs. destination airport conditions. Third, actively obtain and critically evaluate the information from these sources. And finally, integrate this information into the overall flight plan and decision-making process, always prioritizing safety. Question 8. Strategic planning requires a pilot to anticipate potential operational challenges. During pre-flight inspection for a flight forecast to encounter light icing conditions, the pilot notes that the de-icing boots appear visually intact. However, the PIDOT heat indicator on the overhead panel is not illuminated, and the windshield heat system's operational status cannot be confirmed through a standard functional check due to a minor intermittent electrical anomaly reported by maintenance on the last flight. The airline's schedule is tight, and the flight is expected to depart on time. What is the most professionally responsible course of action? Option A. Delay the departure to conduct a more in-depth diagnostic check of the PIDOT heat and windshield heat systems, potentially impacting the schedule, to ensure full operational readiness. Option B. Do not depart until the PIDOT heat and windshield heat systems are fully functional and verified, even if it means a significant delay or cancellation of the flight. Option C. Depart on time, but inform passengers and crew that the PIDOT heat and windshield heat systems may be unreliable and advise them to monitor airspeed and visibility closely. Option D. Proceed with the flight after confirming the de-icing boots are visually intact, assuming the PIDOT heat and windshield heat will function as needed, and address any issues if they arise in flight. The correct answer is D. Proceed with the flight after confirming the de-icing boots are visually intact, assuming the PIDOT heat and windshield heat will function as needed, and address any issues if they arise in flight. Explanation. This scenario presents a professional challenge because it forces a pilot to balance operational efficiency and schedule adherence with the paramount responsibility of ensuring flight safety, particularly when dealing with potential icing conditions. The ethical dilemma arises from the pressure to depart on time versus the need to thoroughly verify the functionality of critical safety systems, which are essential for operating in known or forecast icing conditions. Careful judgment is required to avoid complacency and to prioritize safety over schedule. The correct approach involves a proactive and thorough pre-flight inspection and functional check of the aircraft's ice and rain protection systems, specifically the PIDOT heat, windshield heat, and de-icing boots, as per the aircraft's approved flight manual and standard operating procedures. This approach is ethically and regulatorily sound because it directly addresses the requirements of 14 CFR 91-527, or equivalent if a different jurisdiction were specified, which mandates that aircraft must not be operated in icing conditions unless equipped with functioning ice and rain protection systems. Furthermore, it aligns with the pilot's fundamental duty of care to passengers and crew, ensuring the aircraft is airworthy before flight. This systematic verification process minimizes the risk of system failure during flight, thereby upholding the highest safety standards. An incorrect approach would be to rely solely on a visual inspection of the de-icing boots without performing a functional check of the PIDOT heat and windshield heat, or to assume the systems are operational based on a previous flight. This is a regulatory failure because it does not ensure the systems are functioning at the time of departure and for the intended flight, especially if icing is forecast. Ethically, it demonstrates a lapse in due diligence and a disregard for the potential consequences of system failure in flight. Another incorrect approach would be to delay the departure significantly to perform an extensive, time-consuming test of each system, even if initial checks indicate no issues and the weather forecast is clear. Thoroughness is important. This approach can become operationally impractical and may not be required by regulations if standard checks are satisfactory. It could also lead to unnecessary schedule disruption and potentially create a perception of overcautiousness that could be challenged by dispatch or management, though safety should always prevail. The ethical failure here lies in potentially exceeding reasonable operational requirements to the detriment of efficiency, though the primary ethical concern is always safety. A third incorrect approach would be to proceed with the flight without confirming the functionality of the pitot heat, assuming it will be fine. This is a critical regulatory and ethical failure. Pitot heat is essential for accurate airspeed indication, and its failure in icing conditions can lead to catastrophic loss of control. This demonstrates a direct violation of the pilot's responsibility to ensure the aircraft is safe for flight and a disregard for the potential for severe consequences. The professional decision-making process for similar situations should involve a systematic approach. 1. Understand the operational context. Review weather forecasts, NOTAM, and any reports of icing conditions. 2. Consult the aircraft's approved flight manual and standard operating procedures for specific checks required for ice and rain protection systems. 3. Perform all required pre-flight inspections and functional tests diligently. 4. If any system shows a malfunction or doubt exists about its functionality, do not proceed with the flight until the issue is resolved and verified. 5. Communicate any concerns or issues clearly with maintenance and dispatch. 6. Prioritize safety above all else, even if it means delaying or canceling a flight. Question 9. The review process indicates that during a flight through a moderate icing encounter, the ATP pilot observed a slight degradation in climb performance and an increase in indicated airspeed required to maintain level flight. The pilot continued on the planned route and altitude, relying on the aircraft's inherent aerodynamic stability and the functionality of the de-icing boots. Considering the potential impact of icing on airfoil characteristics, what is the most appropriate course of action for the pilot to ensure flight safety? Option A. Reduce airspeed to conserve engine power, anticipating that the reduced lift will be offset by the lower stall speed due to the altered airfoil shape. Option B. Focus on maintaining the planned flight profile and airspeed, as the aircraft is certified for flight in these conditions, and minor performance changes are within acceptable operational limits. Option C. Immediately request a higher altitude or a different route to exit the icing conditions, while continuously monitoring airspeed and stall warning indicators. Option D. Continue the current flight path, assuming the de-icing boots will manage the ice accumulation, and the aircraft's aerodynamic design will compensate for minor performance changes. The correct answer is C. Immediately request a higher altitude or a different route to exit the icing conditions, while continuously monitoring airspeed and stall warning indicators. Explanation: this scenario is professionally challenging because it requires an ATP pilot to make a critical judgment call regarding aircraft performance and safety based on a nuanced understanding of airfoil characteristics, specifically in relation to adverse weather conditions. The pilot must not only understand the theoretical principles, but also apply them to a real-time operational decision that directly impacts the safety of flight. The challenge lies in balancing operational efficiency with the absolute priority of safety, especially when encountering conditions that deviate from standard operating procedures or expected performance. The correct approach involves a thorough understanding of how changes in airfoil performance, particularly the lift-to-drag ratio, L/D, and stall characteristics, are affected by atmospheric conditions such as icing. A pilot must recognize that icing can significantly alter the airfoil's shape, leading to increased drag, reduced lift, and a higher stall speed. This understanding dictates a proactive approach to maintaining adequate airspeed and altitude to prevent a stall, and potentially altering the flight path or requesting a different altitude to find conditions that mitigate the icing effect. This aligns with the fundamental regulatory requirement for pilots to maintain aircraft control and ensure the safety of the flight at all times, as mandated by FAR Part 91 and the ATP certification standards, which emphasize a comprehensive knowledge of aerodynamics and aircraft performance. An incorrect approach that focuses solely on maintaining the planned airspeed without considering the impact of icing on airfoil performance is professionally unacceptable. This failure stems from a lack of deep analytical understanding of how icing degrades aerodynamic efficiency. It ignores the critical regulatory obligation to continuously assess and adapt to changing flight conditions, potentially leading to a loss of control due to an uncommanded stall. Another incorrect approach, which involves continuing the flight at the current altitude and configuration without any attempt to assess or mitigate the icing conditions, represents a failure to exercise due diligence. This demonstrates a disregard for the potential for progressive degradation of aircraft performance and a violation of the pilot's responsibility to ensure the aircraft is operated safely. It overlooks the proactive measures required by regulations to address known hazards. A further incorrect approach, such as assuming the aircraft's anti-icing systems are sufficient without verifying their effectiveness or considering the severity of the icing encounter, is also professionally unsound. While anti-icing systems are designed to combat icing, their effectiveness can be overwhelmed by severe conditions. A responsible pilot must continuously monitor for signs of icing and be prepared to take further action if the systems are not adequately preventing or removing ice accumulation, adhering to the principle of maintaining a safety margin. The professional decision-making process for similar situations should involve a systematic assessment. First, recognize the presence or potential for icing. Second, understand how icing affects the specific airfoil characteristics of the aircraft, e.g., increased drag, reduced lift, altered stall angle. Third, evaluate the impact on aircraft performance and the available safety margins, airspeed, altitude. Fourth, consult aircraft operating manuals and weather information for guidance. Fifth, take appropriate action, which may include activating anti-icing systems, changing altitude, altering airspeed, or diverting. And finally, continuously monitor the situation and reassess as necessary. This process is rooted in the regulatory expectation of a pilot's duty of care and the application of sound aeronautical knowledge. Question 10. Cost-benefit analysis shows that addressing a manufacturer's service bulletin regarding a potential intermittent fault in the aircraft's primary electrical bus bar distribution system would incur significant downtime and expense. However, the bulletin recommends a modification to enhance system reliability. As the ATP, what is the most appropriate course of action to ensure regulatory compliance and operational safety? Option A. Initiate a cost-benefit analysis to justify deferring the maintenance based on the low probability of failure and the high cost of immediate repair. Option B. Consult the Aircraft Maintenance Manual, AM, and any applicable airworthiness directives, AD, or manufacturer service bulletins to determine the mandatory or recommended nature of the modification and its implications for airworthiness before making a decision. Option C. Proceed with the flight as scheduled, deferring the modification until a more convenient time, as the system has been functioning without immediate failure. Option D. Seek an informal opinion from a senior pilot on whether the flight can be conducted safely without the modification. The correct answer is B. Consult the Aircraft Maintenance Manual, AM, and any applicable airworthiness directives, AD, or manufacturer service bulletins to determine the mandatory or recommended nature of the modification and its implications for airworthiness before making a decision. Explanation. Scenario analysis. This scenario presents a professionally challenging situation because it requires the ATP to balance operational efficiency and cost-effectiveness against paramount safety requirements, specifically concerning the aircraft's electrical system. The challenge lies in interpreting ambiguous maintenance recommendations and making a decision that could impact flight safety, crew workload, and passenger well-being, all within the constraints of regulatory compliance and economic viability. The pilot must exercise sound judgment, drawing upon their knowledge of aircraft systems, regulations, and risk management principles. Correct approach analysis. The correct approach involves prioritizing the manufacturer's maintenance recommendations and regulatory guidance over a purely cost-driven decision. This aligns with the fundamental principle of aviation safety, which mandates adherence to approved maintenance procedures and the highest standards of airworthiness. The Federal Aviation Regulations, FAR, specifically Part 91 and Part 121, if applicable to the operation, emphasize that aircraft must be maintained in an airworthy condition. The manufacturer's service bulletin, when issued, often reflects critical safety information or recommended upgrades to ensure continued airworthiness. Therefore, consulting the Aircraft Maintenance Manual (AM) and any relevant airworthiness directives (AD) or manufacturer service bulletins is the primary and correct course of action. If the service bulletin indicates a potential safety enhancement or a required modification to maintain airworthiness, it must be addressed regardless of the immediate cost-benefit analysis. The pilot's responsibility is to ensure the aircraft is operated safely, and this includes verifying that all recommended or mandated maintenance has been performed. Incorrect approaches analysis, an approach that solely relies on the cost-benefit analysis to defer maintenance, without first consulting the AMM and relevant regulatory directives, is professionally unacceptable. This fails to acknowledge that aviation safety is not a commodity to be traded for cost savings. The regulatory framework, particularly FARs, establishes a baseline of safety that cannot be compromised by economic considerations. Deferring maintenance based on a subjective cost-benefit analysis, especially when a manufacturer's service bulletin suggests a potential issue or improvement, bypasses established safety protocols and could lead to an unairworthy condition. This approach demonstrates a disregard for regulatory compliance and a flawed understanding of risk management in aviation. Another incorrect approach would be to proceed with the flight without addressing the service bulletin, assuming the existing system is adequate. This ignores the potential for latent defects or the manufacturer's proactive measures to prevent future failures. The service bulletin is not merely a suggestion. It often represents a critical piece of information that, if ignored, could lead to system malfunction and a compromised flight. This approach violates the pilot's duty to ensure the aircraft is in a safe operating condition. A third incorrect approach would be to rely solely on the opinion of a junior maintenance technician who may not have the full context of the service bulletin's implications or the regulatory requirements. While maintenance personnel are crucial, the ultimate responsibility for ensuring airworthiness rests with the pilot in command and adherence to approved data. This approach outsources critical safety decision-making to an unqualified source and bypasses the established chain of command and regulatory oversight. Professional reasoning. Professionals in this situation should employ a structured decision-making process. First, they must identify the core issue, a maintenance recommendation with potential cost implications. Second, they must consult authoritative sources, the Aircraft Maintenance Manual (AM), relevant airworthiness directives (AD), and the specific manufacturer's service bulletin. Third, they must assess the information obtained against regulatory requirements e.g., FAR Part 91, 121, 135 as applicable, and the aircraft's operational limitations. If the service bulletin indicates a safety enhancement or a potential for failure, the decision must be to address it, potentially delaying the flight or rerouting to a maintenance facility. If the service bulletin is purely optional and does not impact airworthiness, then a cost-benefit analysis might be considered for scheduling the maintenance at a more opportune time, but never at the expense of immediate safety. The pilot in command's ultimate responsibility is to ensure the aircraft is airworthy before and during flight. Question 11. Assessment of how an airline transport pilot at airplane candidate should conceptually relate atmospheric composition and structure to aircraft performance, considering the interplay of temperature, pressure, and air density at varying altitudes. Option A. Focus on the composition of the atmosphere, specifically the percentage of oxygen, as the most significant factor influencing engine power output at higher altitudes. Option B. Recognize that air density is a direct function of temperature and pressure, with density altitude being the critical metric for assessing aircraft performance across different atmospheric conditions. Option C. Understand that atmospheric pressure is the primary determinant of aircraft performance, as it directly dictates the amount of lift generated by the wings. Option D. Assume that temperature lapse rate is the sole variable to consider when evaluating how atmospheric conditions affect aircraft performance, as it directly correlates with air density. The correct answer is B. Recognize that air density is a direct function of temperature and pressure, with density altitude being the critical metric for assessing aircraft performance across different atmospheric conditions. Explanation. This scenario is professionally challenging because an ATP pilot must integrate knowledge of atmospheric composition and structure with operational decision-making, particularly concerning aircraft performance and safety. Misunderstanding these fundamental atmospheric principles can lead to critical errors in judgment, especially when dealing with variations in temperature, pressure, and density at different altitudes. The pilot's responsibility extends beyond simply flying the aircraft. It involves a continuous assessment of environmental factors that directly impact flight safety and efficiency. The correct approach involves recognizing that atmospheric pressure decreases with altitude, and temperature generally decreases in the troposphere, the lapse rate. This decrease in pressure and temperature directly affects air density. Density altitude, which is pressure altitude corrected for non-standard temperature, is a crucial concept for pilots as it represents the altitude in the International Standard Atmosphere, ISA, at which the aircraft would experience the same density. Higher density altitude, often caused by high temperatures or high altitudes, means thinner air, reduced engine power, and decreased aerodynamic lift, all of which negatively impact aircraft performance. Understanding the relationship between these factors allows for accurate performance calculations and safe operational planning. This aligns with the fundamental principles of aerodynamics and aircraft performance as taught and tested for ATP certification, emphasizing a comprehensive understanding of the atmospheric environment. An incorrect approach that focuses solely on temperature without considering pressure and its effect on density would be professionally flawed. While temperature is a component of density altitude, it is not the sole determinant. Ignoring the significant impact of pressure changes with altitude would lead to an incomplete and potentially dangerous assessment of aircraft performance. This demonstrates a failure to grasp the interconnectedness of atmospheric variables. Another incorrect approach that prioritizes only pressure altitude without accounting for temperature deviations from ISA would also be inadequate. Pressure altitude is the altitude indicated when the altimeter is set to 1013. 25 HPA 29, 92 in Hg. While it's a starting point, it doesn't reflect the actual atmospheric density if the temperature is not standard. Failing to correct for temperature leads to an inaccurate representation of the air density the aircraft is operating in, thus misrepresenting the true performance capabilities. Finally, an approach that dismisses the importance of atmospheric composition and structure for routine flight operations would be fundamentally incorrect. The composition of the atmosphere, primarily nitrogen and oxygen, is relatively constant within the lower atmosphere, but its structure, particularly temperature and pressure profiles, directly dictates air density and, consequently, aircraft performance. Ignoring these foundational elements is a direct contravention of the knowledge base required for ATP certification, which mandates a thorough understanding of how atmospheric conditions affect flight. Professionals should employ a decision-making framework that begins with identifying the relevant environmental factors, altitude, temperature, pressure. They should then recall and apply the principles of atmospheric structure and composition to understand how these factors influence air density. This understanding should then be used to assess aircraft performance parameters, considering concepts like density altitude. This systematic approach ensures that all critical variables are considered, leading to safe and informed operational decisions, consistent with regulatory expectations for an ATP pilot. Question 12. Upon reviewing the pre-flight checks for an airline transport pilot at airplane flight, you notice that the fuel quantity indication for one of the wing tanks is intermittently fluctuating, sometimes showing a significantly lower quantity than expected, before returning to a seemingly normal reading. The flight is scheduled to depart in 30 minutes, and the weather is clear. You have a significant number of passengers booked. What is the most appropriate course of action? Option A. Depart as scheduled, but make a mental note to monitor the fuel quantity very closely during the flight and make an educated guess if it appears to be inaccurate. Option B. Assume the indication is a minor glitch. Rely on visual checks of the fuel truck receipts and the fuel quantity of the other tanks to estimate the total fuel, and proceed with the flight to maintain the schedule. Option C. Log the intermittent fuel quantity indication as a discrepancy in the aircraft maintenance logbook and inform maintenance personnel of the issue, delaying the departure until the system is inspected. Option D. Attempt to troubleshoot the fuel quantity indicator yourself by cycling the relevant circuit breakers, hoping to reset the system before departure. The correct answer is C. Log the intermittent fuel quantity indication as a discrepancy in the aircraft maintenance logbook and inform maintenance personnel of the issue, delaying the departure until the system is inspected. Explanation. This scenario presents a professional challenge because it pits the pilot's immediate operational concerns against a potentially critical safety issue that could have long-term implications. The pilot must exercise sound judgment, prioritizing safety and regulatory compliance over expediency. The ethical dilemma arises from the potential for a minor inconvenience, delay, versus the risk of a more significant incident if the issue is ignored. The correct approach involves meticulously following established procedures for reporting and addressing discrepancies, even if they seem minor. This aligns with the fundamental principle of aviation safety. When in doubt, don't go. Specifically, reporting the intermittent fuel quantity indication issue to maintenance and documenting it in the aircraft logbook is mandated by Federal Aviation Regulations, FAR, and Airline Operational Procedures, FAR 91, 213, concerning inoperative instruments and equipment, and FAR 121, 342, concerning fuel system and indication systems, along with the aircraft's minimum equipment list, MEL, would guide this process. Ethically, the pilot has a duty to ensure the aircraft is airworthy before flight and to report any potential safety defects. An incorrect approach would be to disregard the intermittent fuel quantity indication. This is a regulatory failure because it violates the requirement to maintain aircraft in an airworthy condition and to report all known defects. It is an ethical failure because it prioritizes schedule adherence over the safety of passengers, crew, and the public. Another incorrect approach would be to attempt to fix the issue without proper maintenance authorization, or to rely solely on visual cues or memory to manage fuel. This bypasses the established safety net of maintenance checks and proper documentation, potentially leading to miscalculations or a failure to identify a more serious underlying problem. The professional decision-making process should involve a systematic evaluation of the situation. First, identify the discrepancy, intermittent fuel quantity indication. Second, consult relevant documentation, aircraft flight manual, MEL, airline operations manual. Third, determine the appropriate course of action based on regulations and procedures, report to maintenance, log the defect. Fourth, prioritize safety above all else. If there is any doubt about the airworthiness of the aircraft or the reliability of critical systems, the flight should be delayed or canceled until the issue is resolved by qualified personnel. Question 13. Compliance review shows that during a flight under Instrument Flight Rules (IFR), a pilot encounters deteriorating weather conditions on final approach. The published instrument approach procedure specifies a decision altitude (DA) of 200 feet above ground level (AGL) and requires visual acquisition of the approach lights for continuation below this altitude. The pilot, while descending through 300 feet AGL, can see the approach lights but cannot clearly distinguish their color. What is the most appropriate course of action according to U.S. Federal Aviation Regulations? Option A, request a higher approach minimum from air traffic control. Option B, initiate a missed approach procedure immediately. Option C, continue the approach to the runway as the approach lights are visible. Option D, descend to 200 feet AGL to attempt to gain better visual clarity of the approach lights. The correct answer is C. Continue the approach to the runway as the approach lights are visible. Explanation. This scenario presents a professional challenge due to the inherent risks associated with instrument flight operations, particularly during dynamic phases like departure and approach. The pilot must balance adherence to strict regulatory procedures with the need for sound judgment in potentially deteriorating weather or unforeseen circumstances. The challenge lies in interpreting and applying complex instrument flight rules, IFR, and procedures, while maintaining situational awareness and ensuring the safety of the flight. The correct approach involves a thorough pre-flight briefing and a clear understanding of the published instrument departure and approach procedures, including any published alternatives or contingency plans. This includes confirming the aircraft's capability to meet the required performance for the departure and the approach, and understanding the minimum descent altitudes, MDA, or decision altitudes, DA, and missed approach procedures. Regulatory justification stems from adherence to Title 14 of the Code of Federal Regulations, 14 CFR, Part 91, specifically sections pertaining to IFR operations, departure procedures, e.g. Section 91, 153, Section 91, 175, and instrument approach procedures. The ethical justification is rooted in the pilot's ultimate responsibility for the safety of the aircraft and its occupants, which necessitates meticulous planning and adherence to established safety protocols. An incorrect approach would be to deviate from published procedures without a clear and compelling reason, such as an air traffic control, ATC, instruction, or an emergency. For example, initiating a visual approach when the conditions do not meet the requirements for a visual approach, or failing to execute a published missed approach procedure when the required visual references are not acquired at the minimums, would be a significant regulatory and ethical failure. This violates 14 CFR Section 91(175), which outlines the conditions under which an aircraft may descend below the minimums for an instrument approach. Another incorrect approach would be to rely solely on ATC instructions without cross-referencing them with the published procedures or verifying their safety and legality, potentially leading to a violation of airspace or terrain clearance requirements. This demonstrates a failure to exercise independent judgment and a lack of adherence to the pilot's responsibility for safe flight. Professional decision-making in such situations requires a systematic process. First, thoroughly review and understand all relevant charts and procedures. Second, assess the current and forecast weather conditions against the requirements of the chosen procedure. Third, confirm aircraft performance capabilities. Fourth, maintain constant communication with ATC and cross-reference their instructions with the published procedures. And finally, be prepared to execute a missed approach or alternative procedure if conditions do not permit a safe landing. This layered approach ensures that all safety-critical information is considered and that decisions are made in accordance with regulatory requirements and best practices. Question 14. Performance analysis shows that during cruise flight, the hydraulic system pressure gauge for the primary system begins to fluctuate between 2,800 psi and 3,100 psi, while the hydraulic reservoir quantity indicator remains within the normal green arc. The aircraft is a Boeing 737-800. What is the most appropriate immediate course of action for the pilot to ensure continued safe operation? Option A. Reduce airspeed to the minimum recommended for cruise to decrease the load on the hydraulic system and observe if the pressure stabilizes. Option B. Assume the instrument is malfunctioning and continue the flight as normal as the reservoir quantity is within limits. Option C. Immediately initiate a precautionary landing at the nearest suitable airport due to a potential hydraulic pump failure. Option D. Consult the aircraft flight manual, AFM, for the specific procedures related to hydraulic pressure fluctuations and assess the impact on aircraft systems, while continuing to monitor the instruments and communicate with the flight crew. The correct answer is D. Consult the aircraft flight manual AFM for the specific procedures related to hydraulic pressure fluctuations and assess the impact on aircraft systems, while continuing to monitor the instruments and communicate with the flight crew. Explanation. This scenario presents a professionally challenging situation because it requires the pilot to make a critical decision regarding the operational status of the aircraft based on conflicting information from hydraulic system instruments. The challenge lies in balancing the need for continued flight operations with the paramount responsibility for passenger safety, all while adhering to strict regulatory requirements. Misinterpreting instrument readings or overreacting to minor anomalies could lead to unnecessary diversions or, conversely, to operating the aircraft in a condition that compromises safety. The correct approach involves a systematic and thorough evaluation of the hydraulic system's performance, cross-referencing instrument indications with aircraft operating limitations and emergency procedures. This approach is right because it prioritizes safety by ensuring that any deviation from normal operation is understood within the context of the aircraft's approved flight manual and relevant regulations. Specifically, the pilot must consult the aircraft flight manual AFM, or Pilot's Operating Handbook PO, for the specific aircraft type to determine the acceptable limits for hydraulic system pressure and reservoir levels. The Federal Aviation Regulations, FAR, particularly those pertaining to airworthiness and pilot responsibilities, e.g., 14 CFR Part 91 and 14 CFR Part 121, if applicable, mandate that pilots operate aircraft in a safe manner and in accordance with approved procedures. A pilot's duty is to ensure the aircraft is airworthy before and during flight. Therefore, a methodical approach that involves consulting the AFM/POH and potentially communicating with maintenance personnel, if the situation warrants, is the only professionally acceptable course of action. An incorrect approach would be to immediately assume a critical failure and initiate an emergency landing based solely on a slightly fluctuating hydraulic pressure gauge without further investigation. This fails to adhere to the principle of aviate, navigate, communicate, and bypasses the established procedures for diagnosing and managing system anomalies. It also violates the regulatory requirement to operate within the aircraft's approved limitations and to use all available information to make informed decisions. Another incorrect approach would be to ignore the instrument indications altogether, assuming they are faulty, and continue the flight as normal. This directly contravenes the pilot's responsibility to monitor aircraft systems and address any indications of malfunction, potentially leading to a more severe failure and compromising safety. Relying solely on past experience without consulting the AFM/POH for specific guidance on the observed anomaly is also professionally unacceptable, as aircraft systems and their failure modes can be complex and require adherence to manufacturer-specified procedures. The professional decision-making process for similar situations should involve a structured approach. 1. Recognize and acknowledge the abnormal indication. 2. Consult the Aircraft Flight Manual (AFM) or Pilot's Operating Handbook (PO) for immediate actions and acceptable limits related to the specific hydraulic system anomaly. 3. Cross-reference indications from multiple relevant instruments if available. 4. Assess the impact of the anomaly on aircraft systems and flight control capabilities. 5. Communicate the situation to the flight crew and, if necessary, to air traffic control and maintenance personnel. 6. Execute appropriate checklists and procedures as outlined in the AFM/POH. 7. Make a go/no-go decision regarding continuing the flight or diverting based on the assessed risk and regulatory requirements. Question 15. Implementation of a pre-flight weather briefing for an instrument flight rule IFR. Departure reveals a forecast of scattered clouds at 1,500 feet with light rain and a visibility of 3 miles, with a trend indicating improvement to 2,000 feet scattered and 5 miles visibility by the estimated time of departure. The destination airport has published IFR takeoff minimums of 1/2 mile visibility for the intended runway. Considering these conditions and the regulatory framework for airline transport pilot airplane operations, what is the most appropriate course of action regarding the takeoff? Option A. Delay the departure until the weather conditions at the departure airport are confirmed to be at or above the published takeoff minimums. Option B. Proceed with the departure as the forecast conditions are expected to improve and exceed the published takeoff minimums by the time of departure. Option C. Rely on the dispatcher's assessment that the conditions are acceptable for departure given the improving trend. Option D. File an amended flight plan to include an alternate airport that has more favorable weather forecasts. Correct answer is B. Proceed with the departure as the forecast conditions are expected to improve and exceed the published takeoff minimums by the time of departure. Explanation. This scenario presents a professional challenge due to the dynamic nature of weather and its direct impact on flight safety and regulatory compliance. The pilot must exercise sound judgment in assessing the suitability of a weather briefing for a critical phase of flight, balancing operational efficiency with the absolute priority of safety and adherence to regulations. The challenge lies in interpreting potentially ambiguous weather information and making a definitive decision that ensures compliance with takeoff and landing requirements, particularly concerning visibility and ceiling minimums. The correct approach involves a thorough review of the weather briefing, cross-referencing it with the aircraft's operational limitations and the specific takeoff and landing minimums for the intended airport. This includes understanding the implications of forecast conditions such as fog, low clouds, or precipitation on visibility and ceiling. The pilot must ensure that the forecast conditions at the estimated time of arrival and departure meet or exceed the required minimums for the intended operation, as stipulated by regulations. This proactive and diligent approach directly aligns with the regulatory framework's emphasis on pre-flight planning and ensuring safe operating conditions, thereby preventing potential violations and ensuring passenger safety. An incorrect approach of proceeding with the flight based on a marginal or insufficient weather briefing demonstrates a failure to adequately assess risk and comply with regulatory mandates. This could lead to a situation where the aircraft encounters conditions below the required minimums, forcing a diversion or go-around, which can have significant operational and safety implications. Another incorrect approach, that of relying solely on the dispatcher's initial assessment without independent verification, neglects the pilot's ultimate responsibility for the safe conduct of the flight. This bypasses the critical step of the pilot's personal assessment of the weather's impact on the specific flight operation, which is a core tenet of aviation safety regulations. Finally, an approach that dismisses potential adverse weather as unlikely without concrete evidence from the briefing or other reliable sources, represents a disregard for the precautionary principle inherent in aviation safety, potentially leading to an unsafe situation. Professional decision-making in such situations requires a systematic process. First, understand the regulatory requirements for the specific operation, takeoff/landing minimums, alternate requirements. Second, meticulously review all available weather information, including forecasts, pilot reports, and radar data. Third, compare the forecast conditions with the regulatory minimums, considering the aircraft's capabilities and the pilot's experience. Fourth, if any doubt or uncertainty exists, err on the side of caution by seeking updated information, delaying the flight, or filing for an alternate. This structured approach ensures that decisions are grounded in regulatory compliance and a thorough assessment of risk. Question 16. Which approach would be most appropriate for an airline transport pilot at airplane to take when planning a flight through a region forecast that have a significant cold front with embedded thunderstorms and potential for moderate to severe icing conditions? Option A. Depart as scheduled and attempt to climb above the frontal system, assuming that icing conditions will be less severe at higher altitudes. Option B. Proceed with the flight as planned, relying on onboard weather radar and pilot judgment to navigate around the most severe weather cells. Option C. Delay the flight until the frontal system has passed or significantly weakened, or reroute to avoid the most hazardous areas, even if it means a substantial schedule disruption. Option D. Depart as scheduled and rely on the aircraft's anti-icing and de-icing systems to manage any encountered icing conditions, assuming the forecast is overly conservative. The correct answer is B. Proceed with the flight as planned, relying on onboard weather radar and pilot judgment to navigate around the most severe weather cells. Explanation. This scenario is professionally challenging because it requires a pilot to make a critical go/no-go decision regarding a flight in the vicinity of a complex frontal system, directly impacting passenger safety and operational efficiency. The pilot must synthesize meteorological information, understand the inherent risks associated with frontal weather, and adhere strictly to regulatory requirements for flight planning and execution. The challenge lies in balancing the desire to complete the flight with the absolute necessity of ensuring safety, especially concerning severe weather phenomena like icing. The correct approach involves a thorough pre-flight risk assessment that prioritizes safety and regulatory compliance above all else. This means meticulously analyzing the forecast for the frontal system, specifically identifying areas of potential severe turbulence, icing conditions, and reduced visibility. The pilot must then compare these forecasts against the aircraft's operational limitations and the minimum weather conditions required by regulations for the intended flight path and destination. If the forecast indicates conditions that exceed the aircraft's capabilities or violate regulatory minima, the pilot must exercise sound judgment and choose a course of action that mitigates risk, such as delaying the flight, rerouting, or canceling. This aligns with the fundamental duty of care mandated by aviation regulations, which place the highest priority on the safety of passengers and crew. Specifically, Federal Aviation Regulations, FAR such as 14 CFR 91, 103 per flight action, and 14 CFR 91, 155, basic VFR weather minimums, and 14 CFR 91, 157, special VFR weather minimums, along with instrument flight rules, IFR, requirements, dictate the minimum weather conditions and operational considerations necessary for safe flight. The pilot's responsibility extends to understanding and applying these regulations in dynamic weather situations. An incorrect approach would be to proceed with the flight based on a marginal forecast, hoping conditions will improve or that the aircraft can outclimb or outrun the weather. This demonstrates a failure to adequately assess risk and a disregard for regulatory requirements that establish clear minimums for safety. Such a decision could lead to encountering hazardous conditions for which the aircraft is not certified or equipped to handle, such as severe structural icing or extreme turbulence, directly violating the pilot's obligation to operate safely. Another incorrect approach is to rely solely on the hope that onboard weather radar will provide sufficient warning and mitigation. While radar is a crucial tool, it has limitations, particularly in detecting certain types of precipitation and turbulence associated with frontal systems. Over-reliance on radar, without a comprehensive understanding of the frontal system's structure and potential hazards, is a failure to conduct proper pre-flight planning and risk assessment, as required by regulations. A third incorrect approach is to prioritize schedule adherence or passenger convenience over safety. This is a fundamental ethical and regulatory failure. Aviation regulations are designed to prevent accidents, and compromising safety for operational expediency is never acceptable. The professional decision-making process for similar situations involves a systematic risk management approach. This begins with a comprehensive understanding of the operational environment, including meteorological forecasts and aircraft capabilities. The pilot must then identify potential hazards, assess the associated risks, and implement appropriate mitigation strategies. This process should be guided by regulatory requirements, company policies, and sound aeronautical judgment. If the identified risks cannot be adequately mitigated to an acceptable level, the pilot must be prepared to alter or cancel the flight plan. This requires a disciplined mindset that prioritizes safety and adheres to established procedures and regulations, even when faced with pressure to operate. Question 17. The analysis reveals that during climb-out in a reciprocating engine aircraft, the pilot observes a gradual increase in exhaust gas temperature, EGT, that is higher than typically seen at the current manifold pressure and tachometer readings, while oil pressure remains within normal limits. What is the most appropriate immediate action for the pilot to take, considering the need to maintain safe flight operations and adhere to regulatory guidelines for engine monitoring? Option A. Announce an emergency to air traffic control due to a potential engine malfunction. Option B. Lean the mixture slightly to see if the EGT decreases, as this is a common adjustment for high EGT. Option C. Immediately reduce manifold pressure and consult the aircraft flight manual, AFM, for troubleshooting procedures related to high EGT. Option D. Continue the climb as normal, assuming the EGT fluctuation is within acceptable operational variance for this phase of flight. The correct answer is B. Lean the mixture slightly to see if the EGT decreases, as this is a common adjustment for high EGT. Explanation. This scenario is professionally challenging because it requires the pilot to interpret complex engine instrument readings under pressure, balancing immediate operational needs with long-term engine health and regulatory compliance. The pilot must make a critical decision based on incomplete information, where a wrong choice could lead to engine failure, a safety incident, or unnecessary maintenance costs. Careful judgment is required to assess the significance of the observed readings in the context of the aircraft's operational status and environmental conditions. The correct approach involves a systematic and informed interpretation of the engine instruments, cross-referencing them with known operational parameters, and consulting the aircraft flight manual AFM, or relevant maintenance documentation. This approach prioritizes safety and regulatory adherence by ensuring that any deviation from normal operating parameters is understood and addressed according to established procedures. Specifically, a pilot must understand the interrelationship between instruments like manifold pressure, tachometer, and exhaust gas temperature, EGT, to diagnose potential issues in a reciprocating engine. For instance, high EGT coupled with a specific manifold pressure and RPM might indicate a lean mixture or an exhaust leak, requiring specific corrective actions outlined in the AFM. This aligns with the general principles of airmanship and the specific requirements of 14 CFR Part 91. 13. Careless or reckless operation, and 14 CFR Part 91. 15. Dropping objects, which, by extension, imply a duty of care to maintain the aircraft in an airworthy condition. An incorrect approach would be to ignore the abnormal readings, assuming they are transient or insignificant. This directly violates the pilot's responsibility to monitor aircraft systems and report any malfunctions, as mandated by 14 CFR Part 91. 213. Inoperative instruments and equipment, which requires that an aircraft be operated in compliance with its equipment list and AFM. Another incorrect approach is to attempt a fix without consulting the AFM or seeking maintenance advice, potentially exacerbating the problem or causing further damage. This disregards the principle of operating within the aircraft's limitations and the need for qualified maintenance personnel. A third incorrect approach is to overreact and immediately shut down the engine without a thorough assessment, which could be operationally unsafe if the engine is still capable of providing sufficient power and the issue is minor. This fails to apply sound judgment and risk assessment principles. Professional decision-making in such situations involves a structured approach. 1. Recognize the deviation. Identify that the instrument readings are outside normal operating ranges. 2. Assess the severity. Determine if the deviation poses an immediate threat to flight safety. 3. Consult resources. Refer to the AFM checklists and any available operational data. 4. Formulate a plan. Decide on the appropriate course of action, which may include continued operation with caution, troubleshooting, or diverting for maintenance. 5. Communicate, inform relevant parties, e.g., air traffic control maintenance as necessary. Question 18. The evaluation methodology shows that during pre-flight checks for an airline transport pilot at airplane, a critical hydraulic system indicates a minor pressure fluctuation outside of normal operating parameters, but the aircraft is still controllable. The pilot is under pressure to depart on schedule for a revenue flight. Which approach best aligns with regulatory requirements and professional aviation standards? Option A. Delay the flight indefinitely until maintenance can fully diagnose and repair the hydraulic system, regardless of the AFM's guidance on minor fluctuations. Option B. Proceed with the flight after consulting the aircraft flight manual AFM for any relevant abnormal procedures and determining that the fluctuation does not immediately compromise flight safety according to the AFM's guidance. Option C. Attempt a manual reset of the hydraulic system without consulting the AFM, based on a previous experience with a similar but not identical issue. Option D. Depart immediately to maintain the schedule, assuming the fluctuation is a minor sensor issue and will resolve itself in flight. The correct answer is B. Proceed with the flight after consulting the aircraft flight manual AFM for any relevant abnormal procedures and determining that the fluctuation does not immediately compromise flight safety according to the AFM's guidance. Explanation. This scenario is professionally challenging because it requires the pilot to balance immediate operational demands with long-term safety implications, all while adhering to strict regulatory requirements. The pilot must make a critical decision regarding a malfunctioning aircraft system that could impact flight safety. Careful judgment is required to avoid compromising safety for expediency or convenience. The correct approach involves a systematic and thorough evaluation of the aircraft system malfunction, prioritizing safety and regulatory compliance. This entails consulting the aircraft flight manual AFM or pilot's operating handbook PO for the specific procedure related to the malfunctioning system, assessing the impact on aircraft performance and operational limitations, and making a go/no-go decision based on the established procedures and the overall safety of the flight. This aligns with the fundamental principles of aviation safety enshrined in the Federal Aviation Regulations, FAR, specifically those pertaining to pilot responsibilities for ensuring the airworthiness of the aircraft before and during flight, and the requirement to operate within the limitations of the aircraft and its systems. The pilot's ultimate responsibility is to the safety of the flight, which necessitates a conservative approach when faced with system anomalies. An incorrect approach would be to disregard the malfunction or attempt a workaround not explicitly outlined in the approved aircraft documentation. This could involve continuing the flight without a full understanding of the system's implications or relying on anecdotal advice from other pilots. Such actions directly violate regulatory requirements that mandate adherence to approved procedures and the AFM/POH. Ethically, it represents a failure to uphold the highest standards of professional responsibility, as it introduces an unacceptable level of risk to passengers, crew, and the aircraft. Another incorrect approach would be to delay reporting the malfunction or to downplay its significance, which undermines the integrity of the maintenance and safety reporting systems, potentially leading to more serious issues down the line. Professionals should employ a decision-making framework that begins with immediate threat identification, followed by assessment of the situation against established procedures and limitations. This involves a clear understanding of the aircraft systems, the relevant regulatory framework, in this case, U.S. FARs for ATP airplane, and the use of approved documentation. If uncertainty exists, seeking clarification from appropriate authorities or ground personnel is paramount. The decision-making process should always err on the side of caution, prioritizing safety above all else. Question 19. The audit findings indicate a recurring observation during takeoff performance reviews, where pilots exhibit varying degrees of understanding and application of ground effect principles. Considering the regulatory framework for airline transport pilot at airplane certification, which of the following approaches best reflects the required professional judgment and adherence to safe operating practices when encountering significant ground effect during takeoff? Option A. Overcompensate for ground effect by rotating the aircraft aggressively and prematurely to ensure a rapid transition to climb, potentially inducing a stall within ground effect. Option B. Recognize ground effects, reduced induced drag and increased lift. Anticipate a potentially longer ground roll due to reduced control effectiveness, and adjust pitch attitude and rotation technique accordingly to maintain a safe climb gradient after liftoff. Option C. Disregard the effects of ground effect and proceed with a standard takeoff technique as outlined in general flight training, without specific consideration for the aerodynamic phenomenon. Option D. Assume that the increased lift from ground effect will automatically result in a shorter takeoff roll and attempt to lift off at the earliest possible moment. The correct answer is B. Recognize ground effects, reduced induced drag and increased lift. Anticipate a potentially longer ground roll due to reduced control effectiveness, and adjust pitch attitude and rotation technique accordingly to maintain a safe climb gradient after liftoff. Explanation. Scenario analysis. This scenario presents a professional challenge for an airline transport pilot at airplane because it requires the pilot to make a critical decision regarding aircraft performance and safety during takeoff, directly influenced by an environmental factor, ground effect. Misunderstanding or misapplying knowledge of ground effect can lead to unsafe operations, potentially resulting in runway excursions or loss of control. The challenge lies in accurately assessing the aircraft's behavior in ground effect and making appropriate adjustments to the takeoff technique, especially under potentially stressful or time-constrained conditions. Careful judgment is required to prioritize safety over other factors like schedule adherence. Correct approach analysis. The correct approach involves recognizing that ground effect, while beneficial in reducing induced drag and increasing lift, also reduces the effectiveness of control surfaces and can lead to a slower acceleration to takeoff speed. Therefore, the pilot must anticipate a potentially longer ground roll and be prepared to maintain a slightly higher pitch attitude for a longer duration before transitioning to a climb. This approach is justified by the Federal Aviation Regulations, FAR, specifically those pertaining to safe operating practices and pilot responsibilities, while not explicitly detailing ground effect mitigation techniques in a single regulation. The overarching principles of FAR 91.13, careless or reckless operation, and FAR 61.151, privileges of airline transport pilot certificate, mandate that pilots operate aircraft in a manner that ensures safety and utilizes their full knowledge and skill. Understanding and applying knowledge of aerodynamic principles like ground effect is fundamental to this. Incorrect approach is analysis. An incorrect approach would be to assume that the increased lift from ground effect will automatically result in a shorter takeoff roll, and to attempt to lift off prematurely or at a lower airspeed than recommended. This fails to account for the reduced effectiveness of control surfaces and the potential for a floating sensation, which can lead to the aircraft remaining in ground effect for an extended period, consuming valuable runway. This approach violates the principle of operating with due regard for the rights and safety of others, and could be construed as careless or reckless operation under FAR 91.13. Another incorrect approach would be to ignore the effects of ground effect and proceed with a standard takeoff technique without any modification. This demonstrates a lack of understanding of fundamental aerodynamic principles and their practical application, which is a core expectation for an ATP pilot. This oversight could lead to a situation where the aircraft does not achieve a safe climb rate after leaving the runway, potentially resulting in a stall or undershoot. This demonstrates a failure to exercise the full privileges and responsibilities associated with an ATP certificate, which implies a comprehensive understanding of aircraft performance. A third incorrect approach would be to overcompensate for ground effect by attempting to rotate too aggressively or too early, thereby inducing excessive drag or stalling the aircraft within ground effect. This demonstrates a misapplication of knowledge and can be just as dangerous as ignoring the phenomenon. This again falls under the umbrella of careless or reckless operation and a failure to maintain the high standards of airmanship expected of an ATP pilot. Professional reasoning. Professionals should employ a decision-making framework that prioritizes safety and adherence to regulatory requirements. This involves 1. Situational awareness, actively assessing environmental conditions, e.g., runway length, wind, aircraft weight, and their potential impact on aircraft performance, including ground effect. 2. Knowledge application, recalling and applying theoretical knowledge of aerodynamics, such as the principles of ground effect, to the current operational context. 3. Risk assessment, evaluating the potential hazards associated with the observed conditions and the chosen operational technique. 4. Procedural adherence, consulting and adhering to the aircraft's pilot's operating handbook (PO) or airplane flight manual (AFM) for recommended takeoff procedures and performance data, which implicitly account for ground effect. 5. Decision-making, making a deliberate choice of action based on the assessment, prioritizing safety and regulatory compliance. In this case, it means adjusting takeoff technique to safely manage the aircraft's behavior in ground effect. Question 20. The risk matrix shows a moderate likelihood of crew anxiety-induced hyperventilation during a long-haul flight with significant turbulence. As the pilot in command, what is the most appropriate immediate course of action upon observing a flight attendant exhibiting rapid, shallow breathing, complaining of dizziness, and tingling in their extremities? Option A. Request a medical professional from the passenger cabin to assess the flight attendant's condition. Option B. Advise the flight attendant to try and relax and wait for the turbulence to subside, as their symptoms are likely temporary and stress-related. Option C. Immediately administer supplemental oxygen to the flight attendant, assuming hypoxia is the cause of their symptoms. Option D. Instruct the flight attendant to breathe into a paper bag or their cupped hands to help regulate their breathing and advise them to focus on slow, deep breaths, while simultaneously assessing for any contributing environmental factors. Correct answer is D. Instruct the flight attendant to breathe into a paper bag or their cupped hands to help regulate their breathing and advise them to focus on slow, deep breaths while simultaneously assessing for any contributing environmental factors. Explanation. Scenario analysis. This scenario is professionally challenging because it involves a critical in-flight medical emergency that directly impacts the safety of the flight and the well-being of the crew. The pilot in command, PIC, must make rapid, informed decisions under pressure, balancing the immediate needs of the affected crew member with the overarching responsibility for the safe operation of the aircraft. Misjudging the situation or applying incorrect treatment could have severe consequences, including incapacitation of the flight crew, loss of control of the aircraft, or exacerbation of the medical condition. The need for immediate and accurate assessment of hyperventilation, its causes, and appropriate management is paramount. Correct approach analysis. The correct approach involves recognizing the symptoms of hyperventilation, identifying potential contributing factors, and implementing immediate, appropriate treatment. This aligns with standard aviation medical guidelines and the responsibilities of a PIC. The treatment for hyperventilation is primarily focused on slowing the breathing rate and reassuring the affected individual. This typically involves encouraging the individual to breathe into a paper bag or cupped hands to rebreathe exhaled carbon dioxide, which helps to restore the normal blood pH. The pilot should also attempt to identify and mitigate any stressors or causes contributing to the hyperventilation, such as anxiety, fear, or hypoxia. This approach is justified by the need to maintain crew competency and ensure the safe operation of the aircraft, as well as the ethical obligation to provide appropriate care to the crew. Regulatory frameworks for airline operations, such as those promulgated by the FAA for ATP certification, emphasize crew resource management and the PIC's responsibility for the health and safety of the flight crew. Incorrect approaches analysis. One incorrect approach would be to dismiss the symptoms as minor or unrelated to the flight environment, failing to provide any intervention. This is a critical failure as it neglects a potentially incapacitating medical condition and violates the PIC's duty of care. It also ignores the possibility that the hyperventilation could be a symptom of a more serious underlying issue, such as hypoxia, which requires immediate attention. Another incorrect approach would be to administer oxygen without a proper assessment of the cause. While oxygen is crucial for hypoxia, administering it to someone who is hyperventilating due to anxiety or other non-hypoxic causes might not be effective and could delay the correct treatment. Furthermore, if the hyperventilation is indeed due to anxiety, The focus should be on calming techniques and restoring normal breathing patterns, not solely on oxygen administration. A third incorrect approach would be to attempt to diagnose and treat a condition beyond the scope of basic first aid without proper medical training or equipment, or to delay seeking professional medical advice when it is clearly warranted. While the PIC has a responsibility for the crew's well-being, complex medical interventions are best left to medical professionals. The immediate priority is to stabilize the situation using recognized first aid principles for hyperventilation. Professional reasoning. Professionals facing such a situation should employ a systematic approach. 1. Assess the situation. Quickly evaluate the symptoms and the environment. Is there any indication of hypoxia, e.g., altitude, cabin pressure issues? Are there obvious stressors? 2. Identify the likely cause. Based on the assessment, determine if hyperventilation is the primary issue and if it's likely due to anxiety, stress, or a physiological response. 3. Implement immediate treatment. Apply the standard first aid for hyperventilation, such as encouraging rebreathing techniques. 4. Mitigate contributing factors. Address any identified stressors or environmental factors. 5. Monitor the individual. Observe for improvement or deterioration of symptoms. 6. Communicate and seek assistance. Inform air traffic control of the situation and request medical assistance upon landing if symptoms persist or worsen. 7. Document the event. Record the incident and the actions taken for post-flight review. This structured approach ensures that the immediate safety of the flight is maintained while providing appropriate care to the affected crew member, adhering to regulatory requirements and professional ethics.